Let's do it.
Ladies and gentlemen, Rex Bear Leak Project, how the heck are you? Hope you're safe and doing well wherever you are. As you can see, I've got my protective face mask on because everybody's freaked out about the swamp gas bug. So I do have not only an EMF blocker, this blocks EMF radiation, but it's also silver lined, which is an antibacterial. Hello, making a time machine with my brother Gareth over here. We're working on it. Today, ladies and gentlemen, we're going to talk about this just bizarre anomaly that's massive. It is absolutely massive, and it seems to be ripping solar systems into pieces, essentially, is what Gareth is telling me. Did I get that? Did I get that right? Something's ripping the solar systems into pieces?
Galaxies.
Galaxies? Whoa.
Galaxies.
That's major, super major. Yeah. So I did want to say real quick, folks, that I want to thank my friends over at virtualshield.com. There is a great opportunity right now if you go to virtualshield.com, if you want to keep your information safe and anonymous. If you go to virtualshield.com/leakproject, you can get a 30-day free trial membership. And after that, it's only $2.50 a month to keep your information secure. It is so easy to use. All you do is you download it. It takes about a minute. Then you push a button and it says on, Virtual Shield on, and then you want to turn it off. You push the button and it turns it off. But what's also great about this is a lot of people, when they search something, it's tailored towards not only what they've looked up in the past, but also the geographical area that they're in. So the location that you are in could oftentimes decide what you're looking up, what you're going to find. If you use Virtual Shield, you can look stuff up from anywhere. You can have an open platform. You could be in Colorado and they would think that you were in Texas or around the world. So check it out, virtualshield.com/leakproject. Okay, let's jump into this, man. I'm going to take the gloves off. I ain't worried about it anymore. All right, swamp gas is not going to get me. All right, what do we got going on? Gareth, you're looking good, man. Good to see you.
Yeah, surviving the apocalypse.
Yeah, it's pretty doomy out here in Colorado, I'll tell you. You got curbside pickup with restaurants. You got drive-through dispensaries. It's really doomy here.
Yeah, you got enough toilet paper?
No, but I do have baby wipes.
Hey,
we're out of toilet paper, but they did have baby wipes. So I was like, we'll go with that. So what's going on, man? Talk to us. You've got a lot to share with us today.
Well, there's quite a detailed topic that probably will take us on a few tangents, and I think it won't answer anything. There's a lot of questions we're going to go through. There's some alternative ideas I've got, but at the end of the day, I think it's going to open your eyes to some of the facts that we keep being presented in terms of distances, in terms of speeds, which actually make you question, what our universe actually looks like. But I'm going to take you through all of that. We're going to start with the mystery of, well, you can actually see, it's back to front. The image behind you is an example of one of these galaxies being ripped apart. And it's a strange one because it is all to do possibly with where it is, the location. But let's dive in, shall we? Let me take control. Yep. And we want that one. And let's present. So some of you might be familiar with the image that you see behind the text here. And the Great Attractor will be part of this discussion because in order to understand what's going on, we need to look at what the Great Attractor is. But before we do that, let's start at the beginning. So M86, which is not the same as M87, which is the one with the black hole image, but M86, which is nearby M87. But it is a galaxy that we have been observing for over 200 years. But the problem is, in all that time we've been observing it, we don't know what it looks like. And if you look at the image, you can see it's sort of blobby. That's the basic, my technical description is it just looks like a blob. And normally when we look at galaxies, obviously the Milky Way, spiral galaxy, there are things called lenticular galaxies, which are sort of stretched out. But this one is very difficult for them to classify. Until recently, and with obviously the advent of better telescopes, the Hubble is able to see things in X-ray. There's Chandra, which is another telescope that is also able to see these things. They were able to take more images of this, and those images revealed something rather interesting. So when you look at this image, so again, here is where we see M86. So that's the same, that part of the blob. But when we look here, we see it there. And what you see behind here is sort of what looks like a streak of material being drawn outwards. But interestingly enough, it's still, I would almost say when you look at this image, there's sort of two halves to it, sort of a curve upwards, and there is also equally a curve down here. And when they examined this, they sort of, I mean, obviously this is the image that they're dealing with. It's not like, you know, the image you can see behind me, which has more clarity in it, but obviously they base what's going on the fact that this must be a galaxy, and therefore, in order for it to have this shape, something must be pulling it apart. So that's the story we're going to sort of look at, and this will lead us into a bit of a rabbit hole, which was going to ask many questions. So let's just start by understanding what M86 is. So M86 is a galaxy that is part of what is called the Virgo cluster, and this is a massive cluster of galaxies. Over 100 galaxy groups, so clusters of galaxies, fit in the Virgo cluster, and it spans about 100 million light years. So it's quite large, and it's located from where we sit. It's about 50 million light years away, which is a significant distance. And what we do know is that the Virgo cluster is moving towards what we call the Great Attractor. And when they analyzed M86's sort of movements, and we'll talk about how they do that later on, but they worked out that this galaxy was moving towards us at over, well, I've written down 500,000 miles per hour, but actually if you use the numbers that they give, you can actually calculate it to be over 2 million miles an hour. That is the speed at which it is moving towards us, but is equally moving across from us as well. And just to give you an understanding of where the Virgo cluster sits, so again, in this image, this is the Virgo cluster over here. So it's a massive cluster of galaxies. And then we sit just to the side of it. And then over on this side here is the Great Attractor. And the Virgo cluster is moving towards that Great Attractor. No, I don't want to do that. And as we sit here, we're also sort of being pulled in that same direction. So we're moving in this direction, and it's moving in that direction towards this Great Attractor. So what on earth is the Great Attractor, you might ask? Well, at the moment, we don't really know. The best theory is that there is something large that sits behind here. So an even larger cluster of galaxies creating sort of a gravitational attraction, which is pulling everything in that direction, a bit sort of like a kitchen sink.
And we're not going to see it just because of all the lights and everything that's in front of it? Is that why we have, or has it been discovered?
No. So indeed, when we look at this, if I just exit this for a second. So the Vela cluster, or where the Great Attractor sits, is behind the Milky Way. So from where we sit, we cannot observe it. So we only see the effect of what's happening with other galaxies sort of moving towards it. So it's our best assumption that it looks something like this. But in all honesty, we don't actually know because we can't see this. What we can see sits over here. So we make many assumptions. But based on the movement of those objects, the assumption is that it's probably about 8 times larger than the Virgo cluster, so 800 to 900 million light years across. But we have no idea how many galaxy groups sit in it. It must be massive in order for it to be pulling the objects that vast distance and accelerating over that speed. But we don't know because we can't see it. Now,
remarkable.
Yeah, I mean, it is remarkable because, again, everything that we observe, so all the galaxies we observe all along here are from where we sit moving towards us. And then when we look in this direction, what we see is them moving away from us. And then we see the ones that sit further behind here moving towards it. So there's sort of like a dance going on in terms of the galaxies moving towards what we assume is towards this point. And, you know, we can talk at some stage, but not today, about these big blue areas, the void areas, but that's a different story. So how do we even measure the distance? How do they know that this galaxy is, you know, 50 million light years away from Earth? Most of, for objects that are that far away from the Milky Way, we use something called redshift. And this assumes that the universe is expanding. So it's back to this story of the Big Bang, which, as you know, I don't particularly believe in. But that idea is that the universe itself is expanding. And as the universe expands, it means that objects are moving further away. And if you assume that it all started at a small point, it means that the objects that are furthest away must be traveling faster. It's like an explosion. Yeah, if everything started at the same point, those further away must be traveling faster. So therefore, when we look at objects, like you stand at the side of a road and you've got a police car that goes past you, or even just a normal car, you'll hear a change in pitch as it goes past. And meow. That's not because the car is making a different noise. It's because as it approaches you, the sound waves get squashed, and as it moves away from you, they get stretched. The same principle happens with light. If an object is moving towards us with enough speed, the light waves get compressed and it'll turn bluer. And if it's moving away from us, it'll get stretched and it turns redder. So they use this by analyzing the galaxies and understanding what a normal galaxy would look like. And this may also be part of the problem. You can identify how it shifted. So by how much it shifted, you can work out how fast it has to travel for that to shift. And then you look at your little map that says, well, if it's traveling at that speed, well, that sort of means it's got to be that far away. Problem here is this object is moving towards us. So how on earth do we know what speed it's going? Because it no longer fits in that beautiful book of everything expanding outwards. There are a number of different ways that we can measure the distances to objects that are further away. And this has its limits in terms of distance, but basically what we're trying to do is identify objects within a galaxy that emit a known amount of light. If you can, like what they call standard candles, and examples are X-ray bursts from neutron stars, tip of the red giant, variable stars, novas, and supernova explosions, because you can sort of make a rough guess as to how much light is given off. And again, the further an object is away, the dimmer it will become. So if you can measure that light, and if you knew it was a nova, then you could estimate how far away it is by how dim it is by the time we receive it. So that's a different way that we can measure the distance to an object. Now, what do we know about M86? Well, when you look at the numbers that they quote, and this is quite interesting, they quote a speed of 1,050 kilometers per second that it is moving towards us. And at the same time, when we look at the sky, so when you observe at night, or when you look at the stars close to us, there are two motions that stars do. One will be towards and away from us. So again, if we look at a star, Arcturus, and we'll talk a little bit about Arcturus in a bit, but that star might be moving towards us or moving away. At the same time, if we observe that star over a prolonged period of time, let's say a year, we'll notice that the star moves across the sky against the background stars. Assuming the stars in the background are far enough away that we could consider them not to move, then we would notice that star would move against the background. And that's where we look at this moving across the sky number. That's what we're referring to. They're measuring how quickly it is moving across the sky. Now, based on these numbers, when they sort of plug them together, they estimate that this M86 is actually orbiting some central object that is causing this pull. And they estimate that based on the numbers that they've got, that it would take 5 billion years for it to complete one orbit. Now that's, I mean, personally, I think that's madness, that you can think that an object is in orbit based on those numbers, and we'll talk a bit how ridiculous the numbers are in a minute. But 5 billion years, according to their book, that's like, you know, a third of the age of the universe would be how long it takes for it to orbit this thing. But okay. Now, the values that you see above here, so this 1,050 and 227, are based on redshift data. That's how they have to obtain that information. Now, some more interesting facts about M86. Again, this image that you see here is actually an X-ray image. We're looking at X-rays from it. So we know that it actually is an X-ray source and also appears to be emitting radio waves as well. Now, that's not necessarily something unusual for galaxies, but again, what we're seeing is those X-rays are coming from some of this material as well. So it's not just the central core, but parts of that material are emitting it as well. Now, what they also detect is the fact that there are hydrogen ions in this stream of gas. So this gas here contains hydrogen ions. And based on all of those facts that they see, what they think is that something called ram pressure stripping is going on. And we'll cover what that is in a minute, but effectively what it is that parts of the material inside the galaxy are being stripped away and sort of pushed behind it. Now, it's not the only one. Again, when you look at the galaxies around it, you'll notice that there are other galaxies that sit in its vicinity that also exhibit similar properties, that this gas being pulled out. So it seems to be happening not just to it, but to other galaxies as well. But the very odd fact is that there are some smaller dwarf galaxies, just like we have dwarf galaxies around the Milky Way, but oddly enough, they're unaffected by this. So they don't seem to be being stripped away. They just seem to go merrily on without any concern whatsoever. So we know that these are moving sort of as a group towards what we think is the great attractor. Again, part of the problem of the story is the fact that this stripping is not consistent across the group. If they're all moving at this speed, you would expect, all of the galaxies to exhibit very similar stripping properties, but they don't. And that's, again, a fact that we'll come back to in a bit. So what is ram pressure stripping? Now, when we normally talk about space, often you kind of assume that it's empty. There's emptiness in between the stars and in between the bits in between galaxies, but that's not the case. In between stars, there is what we call the interstellar medium, and that contains plasma and gases, sometimes in more dense areas and sometimes in less dense areas. And from those gas, eventually, what they believe is that new stars will be born. The same goes in between galaxies. The space in between galaxies isn't just empty vacuum space, but there is material that sits there as well. Now, it's less dense than the stuff that we find inside of the galaxy. But if you imagine when you're sort of wading through water, that the faster you try and push through water, the more pressure that water sort of exerts on yourself. Now you imagine this galaxy is traveling through space, and in between the galaxy, there's sort of gas and material, but then there are more dense stars. And what happens is when you push it through the interstellar medium, normally at a slow speed, we don't believe anything would happen. It sort of just moves along. But if you start to move it fast enough, what happens is the intergalactic media pushes through the galaxy, and the stars themselves are largely unaffected because they're more dense and they're harder to move. But the gas in between sort of gets swept away with that movement of the intergalactic space, and that's why you end up with this sort of plume that is pushed out behind it. That's the principle behind the ram pressure stripping. It's got to move fast enough, and we're talking ridiculous speeds in order for this to work. So it's the drag force that is pulling the material in between the stars. And you might look at it and go, what's the problem with that? Well, part of the problem is that if the galaxy doesn't have this material, it can't generate new stars. It's sort of the lifeblood of the galaxy. And even if we were to consider this, something that does happen, even in an electric universe, this is a problem as well, because that gas that we talk about is part of what we would consider to be the Birkeland currents that connect the stars together. So it's an important property that galaxies have. So there are some problems with this idea of ram pressure stripping. And the first one that we already talked about is the fact that the galaxies don't all have the same shape. They don't all strip away in the same manner. And you would sort of expect that if they're moving through it, that you would see the same sort of plumes behind the majority of the galaxies. And the fact that the dwarf galaxies don't exhibit it, that's another problem as well. Now, it also means that and this is slightly more technical, but the X-ray and the radio emissions from these galaxies is therefore in this model assumed to be purely collisional. So when this intergalactic media smashes into the interstellar medium, that collision causes these X-rays and radio wave emissions that we see. The weird thing is when you look at some of these galaxies around M87, some of them are actually able to replenish that outflow of material, which again shouldn't be possible. Once you strip it away, it should be gone. And that leads to the last point, and that is we've never seen a galaxy that has been totally stripped. All we ever see are these sort of galaxies that are in the process, but we never see the end product. Now, you could argue that we're just unlucky, that we just haven't got there, they haven't had enough time. But I would argue that there are enough examples that you would expect to find some of these that are totally barren of material. Yet we don't find any. So are there alternative ideas to explain what might be going on in this RAM pressure stripping? So there's three concepts that I want to kind of take you through. So comet galaxies, the cosmic web, and then antimatter galaxies. So let's start with comet galaxies. So some of you may be familiar with the concept of an electric comet. So we know that we have comets that orbit around our solar system on a very regular basis. In the mainstream model, these are lumps of ice. But in the electric universe concept, these are actually basically the same as asteroids, but they have a different potential to the environment that they're in. So as they move closer to the sun, that difference in potential starts to grow. And then the star the comet starts to arc like a lamp bulb. If you turn a lamp bulb on, the wire itself is quite thin, but the glow that you see is significantly larger than that. And that's effectively what we believe is happening with comets, that as they live sort of far out where there's a different potential to the inner solar system, and as they come in, that difference in potential starts to build up as they approach a higher potential point, which is the sun. And then the arcing starts to occur on the surface of the comet, and that forms a sheath around it, which is what you see in the image above here. That's the halo of the comet. And that process is like an arcing process. So you have like a discharge going on the surface, and that discharge actually extracts material from the comet surface, which is, you need to consider it more like an asteroid. And certainly when you look at the images of the comets we've been to, they look like rocks. They don't look like lumps of ice. And this material gets ejected, and that's what forms the tail. That material gets sort of thrown out the back as it sort of moves around. And then as the comet moves further away, the potential difference sort of grows down, and the comet becomes less visible until it's far out enough that actually it's back at its normal potential, and it effectively sort of switches off.
Well, let me ask you a question about that then, because I was reading about the comet C 2019 Y4 Atlas, and they don't know how big it is, but they think it's a few miles across. And it's got a atmosphere right now, technically, that's 720,000 kilometers, which is just massive. And I'm going to myself, how in the world does a few miles of ice cause this much trouble? How does a few miles of ice shoot out so much gas that it's half the size of the sun? It doesn't make sense to me.
No, it doesn't make sense. So for an ice lump, I would totally agree. For it to then have an atmosphere, because I presume it's not that close to the sun yet, is massive. But again, if we consider it to be an electrical event, then that arcing process, again, consider a light bulb. When you look at a light bulb, the actual wire inside of the light bulb is incredibly small compared to sort of the glow that it gives off. And it's that glow that we see that we assume is a light bulb, and in fact, it's a really thin wire that actually produces it.
That makes more sense.
Yeah, and at the same time, the material that's being excavated is being thrown behind it. So not only do you have an area around what would be the comet, which is significantly larger, where the plasma is sort of going into glow mode and into arc mode, but then you also have this material that it's ejecting behind it, which effectively is still connected to it, because it's sort of moving along, ejecting this material constantly. So I'm not surprised that what they consider to be the atmosphere is significantly larger. I mean, even the Earth, if you look at the Earth, that in recent studies they've done, they actually worked out that the Earth's atmosphere extends beyond the moon. So when the Apollo missions went to the moon, they never actually technically left Earth's atmosphere. I mean, obviously they landed on the moon, but technically they didn't actually leave our atmosphere. So yeah. So we can take that concept of an electrical comet, and can we apply it to a galaxy? And this is a bit of a stretch, but let's start with this image here. So this image you see in the background here, that is actually what they call the comet galaxy. It is a galaxy, but obviously, if you compare it to this image, it very much looks like a comet, sort of with it drawn out. Now, again, they think in this case, this is an example, again, for them of ram pressure stripping. But if we take this concept of an electrical imbalance, is it possible that galaxies in some parts of the universe have a different potential to the surrounding and therefore will act very much like a comet where the whole thing starts going into glow mode and material ends up being excavated in a similar sort of way? I mean, it'd be quite catastrophic for anything inside of this galaxy. But could it be that that plume that we see behind it is the same plume process, but on just a much larger scale, applying to a whole galaxy? It's possible. You know, this is definitely one of the things that I mean, this is very much an electric universe concept. There are still questions that I have about this. So again, in this example, they would explain the reason that the objects are moving at such a high speed is because this galaxy would then be attracted to something which is a different charge. Just like the reason comets sort of orbit around it, this galaxy would be attracted to something which has a very different charge potential, and that's why it's moving so quickly. And at the same time, because of that charge potential, is why it has a tail as well. But where
Jump
is
in
that
on that.
structure?
Let me
Yeah,
jump in on that. So looking at the Milky Way galaxy, and most galaxies, they're like spirals, right?
yeah.
So potentially, could this be a comet? Could the Milky Way be a comet galaxy, except for it would be spiraling because it's attracted to something as a central point, or is it going out? Is it spiraling out?
No, so the current sort of idea is that the arms spiral in, so the material flows inwards, and then from the center, if that's the plane, it would travel up and around again. So there's like a loop system built into that. I don't think that our galaxy would be in that category of having a different charge potential, because I mean, if you think about what happens to a comet, there is, you know, when you look at the surface of these comets, and again, if we look at Mars as an example of where we potentially see this sort of arcing event, removing vast amounts of material from the surface, you know, it would have devastating consequences for what is inside of that galaxy, and we don't see that in terms of the Milky Way. The Milky Way is quite a peaceful, you know, tranquil place at the moment compared to what we think these comet galaxies might be like.
It reminds me though, one thing that stood out that you said was there's mass that's attracted to something else.
Yeah.
So you've got the entire universe. If you look at it in frequencies and like a magnet, like multiple magnets. Here's one galaxy, and then all of a sudden it picks up this frequency over here. So it's coming towards it like a magnet. And then if we look at the Milky Way and all these arms that go out and stuff, I'm just thinking of the attraction points. There's going to be like loops of attraction points. So it's like it's working infinity and beyond in these circles or something. I'm just grasping it, and I'm attempting to grasp it mathematically, so I can look at it like in an archetypal form, if that makes sense.
Yeah, I mean, at the center of the galaxy, we believe there's like an engine that powers this, which we believe is powered by what we would call a plasmoid. Now, the question would be for me, when you look at this concept of an electric comet galaxy, you know, what is it being attracted to? At the moment, you know, as you point out, everything goes up in different scales. You know, we see the same thing repeated at smaller scales. So if this is being attracted to something even larger, it either has to be, like you say, you know, another galaxy that has an even larger, electrical potential compared to it, or there is some structure that we cannot see that is even larger than a galaxy itself, that in itself powers all of this system. Now, you know, that's total speculation at this point. We have absolutely no evidence to sort of underpin that. But you know, at what point do you stop going up in scales? I don't know. I mean, I
Could
think
it
there's
just be
another way to explain this, but
yeah. Could it just be like the universe itself? If you look at the universe as a circuit board, and then you find a way to create these factors in this circuit board where you have attracting forces. So instead of it having to be larger in mass, maybe it could be the universe itself. And it seems like if you look at something underneath a microscope, the further you look at it, it'll start to disappear, right? It'll come in and out of existence. So maybe there's this, like this duality, this dual force that we don't see with our physical eyes or with the equipment that we have currently, but it acts as like nodes, or it acts as equalizer almost.
Well, I mean, maybe, but we also know that there is.
I'm a conspiracy scientist, folks. I'm a scientist. I'm a conspiracy scientist.
I mean, we do suspect that there are charge imbalances across the universe anyway. We know it's not. So, according to the Big Bang, the universe should look the same in all directions. And clearly it doesn't. So, therefore, they come up with dark matter to explain, the different clumping. But, if we go for an electric universe concept, then, the filamentation structure that we looked at before, and we are going to talk about it in a bit as well, could be carrying charge from one part of the universe to the other. And that movement of charge would create an imbalance between one side and the other. Now, the question then becomes, what powers that? Do you even need to power it? Because all you need to have is a difference on one side versus the other side. Now, people would argue that eventually that should balance out. If you have a cup of cold water and a cup of hot water, and you sort of mix them together, you leave it long enough, and eventually it's lukewarm water. But, is there something else that drives that constantly changing? Is there, in some sense, going back to what you said, is there an underlying structure that actually provides a mechanism whereby that difference in charge can be maintained from one area to another? And, there is a concept that I looked at, which is Tom van Flanders' push gravity concept, which had this concept of an ether where actually, as light travels, that energy gets dissipated into the universe, but that actually gets absorbed into an ether, which is then able to sort of absorb that, and eventually it gives it back somewhere else. So there are concepts that could explain that in a different way. So it is possible, absolutely. And I certainly believe that this is a universe that has that imbalance, absolutely. But I always like to ask why, and sometimes with these you can't quite get to there isn't a reasonable explanation at this point that explains it well enough, and therefore you have to look at lots of different ideas and try and work out which ones fit some of it, and therefore what does it allude to behind the scenes might be going on to cause that.
Right on.
So again, problems with this concept that I see is it requires something to attract it. That's not an impossibility, because, as I said, it could be that there are differences that we just see. The question is, how do they get that? How does that one galaxy end up with a different charge imbalance to ours? Is that just part of where they grew up versus where they are now? Why they're moving in the first place? It raises a lot more questions as well. And the other question that relates to this, again, if we go back to this image, when we observe these galaxies, particularly the ones that we're considering to be Ram stripping, it's a very narrow band that this occurs in. It's not like, everywhere we look, we see this. And again, this is part of the problem with accepting that it is the great attractor that's doing it. Because if a galaxy over here is being attracted there, then surely all of these galaxies everywhere should be experiencing that same force. So therefore, why isn't everything being Ram stripped in the same way? So again, it's trying to understand and explain a way that allows you to have channels where, for some reason, some things are traveling much quicker than other things, and why in the rest of the universe it's just going on at its merry own pace, relatively speaking. So another way to look at this is the cosmic web.
Dude, it's the Borg cube.
It is the Borg cube. I showed my son. He was like, "Oh, that's the Borg cube." I was, well, it sort of looks like the Borg cube, but no, it's not the Borg cube. So we've talked about this before, the fact that everything in the universe is connected by what we call the cosmic filaments, the galactic web. Now, obviously, in mainstream, they believe that this is dark matter that's holding all of these things together. We believe that actually it is plasma that connects all of these things together, and that's obviously why we can't see it. And the question then becomes, is it possible that actually the reason we see these narrow channels and the reason that the galaxies are moving is because they're basically following some of these filaments. They're traveling along these filaments Maybe some move a little bit quicker than other ones. So could that be another way to explain the movement of the galaxies? Problem here is that would require the galaxies to move quicker than the plasma itself. You imagine that they're traveling along a sort of a, just for now, imagine it's a tube, and these galaxies are traveling down this tube. In order for them to be stripped, they've got to travel faster than that plasma. So again, how does that work? Because normally they just sort of follow the flow. Yet here they have to be traveling faster. Yeah.
Could we go back to that image real quick?
Yeah. The
I want
Borg
to point
cube.
something out that I think is fascinating. So, the Jewish tradition. I've got a friend that's Jewish that lives in Israel, and he brought up some people think the cube that they wear is connected to something dark, right? Because it's a cube and it's black, and they're like, man, is that the Borg? But what you just showed was fascinating. What you just showed us is a possible interpretation of the universe. And I just looked up the term on Britannica. The Hebrew tefillin, also spelled tefillin or tefillin, is in the Jewish religious practice one of two small black leather cube-shaped cases containing the Torah text written on parchment, which, in accordance with Deuteronomy, Deuteronomy, 6:8, and similar statements in Deuteronomy 11:18 and Exodus 13:9, are to be worn by the male, I think, on his head or whatever. But dude, the Hebrew language, I remember talking to my friend Diamond from Oppenheimer Ranch, which follows the Electric Universe big time. He's a big fan of that. And he said he did some research where somebody brought up how the Hebrew language they could have got it from like these lightning bolts in the heavens and these certain arcs of electrical phenomena that were going on in the heavens. So they're writing it down on the micro level. And then what you're showing me here, combined with what I just read and the Torah written in this cube, man, that's fascinating. That's like a micro of the macro, possibly. What are your thoughts on that? It's like,
Well, I certainly believe that the ancients knew a lot more than we give them credit for. And I'll show you an image later on. But last time we talked a little about Arcturus and its motion, and the fact that actually, if you look at esoteric and ancient texts, it does imply that we orbit around Arcturus, and it implies that we orbit around the Pleiades. Now, I've actually I spent quite a bit of time making a sort of an animation to show that movement, how we move through space. I measured the distances to a variety of our local stars to actually work out how that movement would actually play out. And when you look at some of those cycles, is something that I'm going to be delving into in more detail. Numbers become really important, and when you start looking at why do we have 24 hours in a day? Why do we use 60 degrees? And then you see those same numbers appearing in the pattern in terms of how many times we orbit around Arcturus and how many times Arcturus then has to orbit around the Pleiades. And you see the same numbers coming out, and you see the constellations pointing in the direction that we're moving. And then you look at it and you go, this is not coincidence. One or two of them you could look at and go, yeah, that's just coincidence. There are so many things that are starting to line up that you look at it and you go, this is knowledge that someone has tried to encode in a way that you can pass it on. And we are foolish enough to think that these are fables and stories that mean nothing. And for me, what it shows is that civilization, as we know it, is far, far older than we give it credit. Because for them to know this information, they either have to be very technologically advanced, or they have to have been observing the heavens for an extremely long time. Take your pick.
Well said.
Either one blows my mind. Yeah.
Yeah, cool. Well, thanks for going back to this image.
Yeah, I mean, I find it a fascinating image. The problem is, if we assume that, again, our galaxies are moving along there, it doesn't entirely explain everything. You could explain it that maybe some of these filaments are intersecting a particular gas cloud, and that the galaxies therefore are slamming into some of those. So that's why you only see some of them happening. But again, you still have to account for the fact that the galaxies have to be moving faster than the plasma. We don't see the plasma actually moving because it's very difficult to detect this sort of plasma in space. We only see the effect when it collides into something or when it becomes energetic. So It's possible, but again, we don't have enough information to really say that this is definitely what might be going on. Now, let's just take one step back here, because this is, I think, the crux of the whole thing is what information do we have that actually says these galaxies are moving? Now, this is maybe a little bit of an extreme statement, because probably the galaxies are moving, but just for a second, let's just go through what the evidence is that supports this concept of the galaxies actually moving. And at the moment, because they are so far away, this is all based on the redshift and the blue shift of data. So this compression or stretching of the light as it moves towards us or goes away from us. Now, based on that information, they sort of extrapolate this orbit that M86 is going around this cluster and will take 5 billion years. But what if the galaxies were not moving at all, or were moving at a normal rate, not this ridiculous speed? Just for a second, let's just do some simple maths. And again, this is the video that I was sort of talking about. This is where I looked at Arcturus and the stars around Arcturus and identified their motion. Again, it's important to understand that in order to measure the distance to an object, anything that's within about 100 light years, we have a variety of different methods that we can measure the distance. As soon as it starts getting any further than that, there are other methods, but obviously the error involved in those methods gets more and more and more. Now, in Arcturus's case, which we believe that we're orbiting around, when I did the calculations, when you look at it, again, we are sort of holding, it is moving towards us at about 121 kilometers per second. So it's about half the speed that M86 is moving. Now, when you look at that, that equates for Arcturus at 0.0006 of a degree across the sky every year. Now, we can measure that. We have instruments that are delicate enough that we can measure that movement. But when we look at M86, that is 1 million times further away. So it would be impossible for us to measure that movement across the sky. Yeah, it's just not possible. So how do they know that it is not only moving towards us, but moving across the sky? Well, I would argue that they don't. Because, again, they're using the redshift and blue shift data in order to work out the speed that it's moving towards us. And, we've already talked about how that works. But when they look at this object, which sits on the other side of the Virgo cluster, so it's moving towards us. We sit here, so we can see that it's moving towards us. And remember, go back to that image that we saw of M86. There's a blob in the center, and you've got sort of an arc of material that's drawing away at the top. That arc, they use that sort of visual image as a reference to sort of say, well, in order for that to happen, it means that the object must be moving sort of across and downwards as well as towards us. They can also tell by looking at the object itself that there is in the Doppler shift a difference between one side of the galaxy and the other. But it's a very small difference. And from that, they therefore infer that there must be a movement across the screen. But obviously what they're trying to do is fit the data to the model that they have. And the model is they see the swept out gas. They see that there are other galaxies that are sort of racing towards us. They see, if they look over at this part, that there are galaxies that are streaming away from us. And therefore they infer that if this is moving towards us and that's moving away from us, it must be sort of following this arc. So they sort of attach this additional motion onto it. But that part of the motion is not really there when you look at it. So the movement towards us, you could argue, that's absolutely, we can see that shift in the frequency. We see a small shift across the object, but whether that is due to the movement in one direction or the other, I would argue that that's not as clear. So they're sort of fitting the data to the model that they have. Also, one of the big things that they assume is that this redshift and blue shift can only be caused by movement. And we know that that is not true. Yet in all the models, again, they go back to this fact, blue shift, redshift must be moving. Now, Holt and Arp believed very much that there was a link between the age of an object and its redshift or blue shift. And he saw that certain objects, doesn't necessarily apply to all of them, But if we look at quasars and some types of galaxies, he said that younger versions would be more redshifted and older ones would become more blue shifted. So there was something going on inside of the object that was changing its properties and making it appear redder or making it appear bluer. Yeah, which is perfectly possible because we're just making the assumption that it should be a particular frequency when we see it either more red or more blue. But that was his concept. But not only that, there is this thing called plasma redshift. And again, ignoring the object itself, but when light travels through space, when it interacts with plasma, that plasma can affect the frequencies of the light as well. And again, they've studied this a lot with lasers, and there's very detailed analysis they've done. But effectively, there are two things that can happen. There can be what they call blue shift and red shift, which occurs when you increase the density. So if the light wave is passing into an area that all of a sudden increases in the density of the plasma, it will cause the light to be sort of compressed and will shift the frequency more to blue. And equally, when it then leaves, it stretches it. So you end up with this process of blue and red shift, depending on the density changes of the light that it travels through. Again, that is not taken into account when we look at these numbers. So is it possible, therefore, that when we look at these charts and we see, galaxies that are redshifted and we see galaxies that are blue shifted, that in fact this may have nothing to do with the movement, or may have very little to do with the movement, and instead is all to do with what's going on in between us and the object itself? So is there some increase in density in the plasma? And again, we can explain that in terms of channels. There could indeed be channels where density is suddenly increasing, which would cause the ionization to increase. So, do you look at the images that we had here differently and say actually where objects are sort of blue shifted, we are seeing a density increase, and where objects are red shifted, we're seeing a decrease in density? Is that a different way to look at this? Again, another thing to consider is when we look at these images of the Ram-stripped galaxies, then most of them have what they call a bow shock, which is like on when you're in a boat, you have like a bow shock in front of it, a pressure wave that occurs in front of it. And that bow shock is where ionization occurs. And again, where we see ionization, we're seeing plasma. So therefore, could the front of this galaxy already start to explain the fact that it's blue shifted, because we've got massive ionization occurring at the front for whatever reason, which would be shifting the light more towards the blue end. So are there channels of high density and low density that actually we need to start taking account of across this image? Now, on top of this, there are some very strange properties that apply to all Ram-stripped galaxies, and that is that they are bluer in color. And not because they're moving towards us, because obviously when we look at some of these channels, there are galaxies that are Ram-stripped that are moving away from us, not just towards us. But those galaxies themselves are bluer in color anyway. And how can that be? How can it be that they're bluer? Well, they explain the fact that they're bluer because they say that these are younger galaxies, and younger galaxies have younger stars, and younger stars in their model, they shine bluer. So therefore, these galaxies are young galaxies. They might be right. That might absolutely be the case. But I would argue, why is it that the only galaxies that are being Ram-stripped are young galaxies? It's a bit ageist, really, isn't it, in terms of galaxies? Surely we would expect it to be equal across any galaxy. There's no special property for a young galaxy that says, strip me, and an old galaxy that says, no, I'm too old. I'm not going to move this fast. So again, it doesn't really make an awful lot of sense when you examine that. So something else, in my mind, something else has to be explaining all of these sort of properties together. Now, another wild thought, and this really is a little bit out there, but in our universe, we consider there should be equal amounts of matter and antimatter that should have been made. If you believe in the Big Bang, there should have been equal amounts of matter and antimatter made at the start of the universe. Yet there isn't. They're vastly different amounts. In fact, you try and find any antimatter in our universe, and the only place you'll find them is in our large accelerators. We can only manufacture it. We can't actually find it. Now, Hannes Alfvén, who's one of the pioneers of the sort of plasma and electric universe concept, he very much believed that antimatter could exist in our universe. And in fact, it could be hiding in plain sight. And he very much saw that the universe created a cell-like structure, and he saw that in the plasma, and he argued the same could happen for matter and antimatter. And in fact, there is this concept called a Leidenfrost layer, which allows antimatter to separate itself from matter and form like a protective barrier which stops it from annihilating. Because normally, if matter and antimatter come together, big explosion, annihilates, destroys itself. He thought that maybe it is possible that you can have antimatter stars and antimatter galaxies that are separated from us with these Leidenfrost layers. Well, if that's the case, what would happen if one of these Leidenfrost layers broke down? Is that a possible explanation of what we see behind us? I mean, it's highly contentious, and there is, Dr. Santilini, I think it was. I did a video on him. He claims to have produced the first telescope to measure antimatter, and he claims to have seen antimatter galaxies. It's quite contentious, I would say. We don't know. It's possible. I don't think it necessarily explains everything, because it doesn't explain the blueness of it. It doesn't necessarily explain why these objects are moving faster. But maybe part of that is true. Maybe part of that isn't true. Who knows? So where does that sort of leave us if we were to sum all of this madness up together? I think the first important thing is that when we look at the data that they present to us, and again, I go back to this, we go all the way back to the data that they provided on M86, where are we? The speeds that it moves across. Where are we? Well, the fact that it's 1,056 kilometers per second it's moving towards us, and 227 that it's moving across from us. I mean, they quote that as a fact, but actually, if you look to the error involved in that measurement, the error probably is larger than the number itself. Yet they are quite comfortable in presenting it as 227, not 200, and I think for me that's. I'm not saying they're necessarily lying, but it's being convenient with the truth, because the truth is that we really don't know. They're making a lot of assumptions based on what they see, and they're presenting it as a fact. And it simply is not a fact. We do not know that these galaxies are A, moving at that speed, or B, moving across the sky at that distance, because they are simply too far away for us to really say that with any accuracy. Now, part of that red and blue shift that we see, I'm sure, is to do with movement. I'm fairly sure that our universe doesn't necessarily sit statically still, but that it does move. But I don't necessarily believe that these galaxies are moving at the ridiculous speed that they quote. And I certainly don't believe that these galaxies are entirely being stripped. I think something else fundamentally different is going on visually when we look at these galaxies that we need to explain. I don't necessarily have the answer. The comet idea is an interesting concept. So is there some imbalance that could explain some of this phenomena? The fact that some of these galaxies are replenishing, I think, is an important point, which means that whatever is going on is not necessarily a final thing. It's a process that they go through. And again, could it be that part of the reason we see more blue shift and red shift is because there are these different density channels across the universe? And therefore, should we start looking at this red shift and blue shift data in a totally different way? Should we start to actually put a different cap on and think maybe it's not just speed, but maybe this is telling us something else about the structure of the universe that at the moment we're simply ignoring? And, for me, that's fundamentally important, is to go back to the basic principle of how accurate is the data, and are the different ways that we can interpret that data which tell us a different story. Because I don't believe that these galaxies are being ripped apart. And the last image I want to show you, for me, just sort of highlights this problem in terms of we have a model and we try and fit everything into this model. So if we flick to this image here, so this, when you look at this image, first of all, you probably look at it and think, I've photoshopped that image because it looks pretty bad. but it's not actually a photoshopped image. It's two different images that are overlaid of the same object. So this is a galaxy, I think it's the D100 galaxy, which is a spiral galaxy, which you can see. And interestingly enough, when they analyzed it in different frequencies, they actually identified that there was this huge plume coming out from this galaxy. And it's actually hydrogen. This is hydrogen ions, they believe, being ejected. But at this stage, we can't really tell in which direction it's moving. So therefore, they see this being injected. So they're kind of like, well,
incredible, man.
It is incredible when you look at it. The distance, I mean, with the distance that we're talking here is huge. And again, how do they explain this? It must be ram stripping, because that's the only thing that could push this gas outwards. And I would argue that this is actually showing us something totally different, because when I look at that galaxy, the galaxy here, to me, that looks pretty much intact. You could argue for some of the other ones, M86, that there was that strange structure. And obviously, we don't have enough resolution to really see that image. But, you could argue that there is some other process going on. But when we look at this image, that's a pristine galaxy. Looks pretty healthy, pretty nice. So what on earth is that jet coming out? And I take you back to that idea that everything is connected across our universe. The idea that there are these filamentation structures that connected. Is that what we're seeing here? Is this the first time that we actually see one of these connecting to a galaxy itself? I mean, I don't know, but that to me is a very narrow band of gas that goes in. That to me does not shout ram stripping, because you would expect it to happen more on the peripheries than at that center core. And so for me, this is a totally different story that we see here. But again, this is pictured as being, it has to be ram stripping. That's what it must be, because that's the only thing that fits their model. And I don't think it is, personally.
This is one of the neatest photos I've seen, showing the possibilities and the different layers of energy and the matrix that we're in, man. Because people sometimes make me laugh when they think that if you don't see it, it's not real, and they don't even see 0.01% of the electromagnetic light spectrum, not even 0.01%. So this proves it.
Yeah, absolutely. And it's also about looking at things in a different way and being open to, and I'm not saying that any of the ideas, some of the ideas that we've covered today are, a little bit out there. But again, if only a small part of what we're talking about is true, then it still radically changes everything that we assume in terms of how the universe actually works. And to shoehorn everything into one model that doesn't necessarily fit, is like you're running out of ideas. It's like you've run out of steam, and therefore, we'll just, it's got to be that. Can't be anything else. Let's just move on. Let's not even do this image. Let's just hide it. Let's not show it at all. And yet here we have this. I mean, this must be hundreds of millions of light years long. This thing. I mean, it's just unbelievable. And yet, look how narrow it stays across that vast distance. And if this is just gas being stripped out, what turbulence is like. If you drop something behind you in a boat, then it gets spread everywhere. The same should be happening if this is ram stripping. It should just be, there's random collisions which should be causing the material to just sort of spurt out. And as it moves further away, that random speed should carry it out in sort of a cone shape going further out. That is not a cone. In no sense of the word is that a cone.
What galaxy is that shooting out of or shooting into?
It's D100. It's a very small galaxy. It's actually, this is a Japanese, the red part you see is a Japanese image that is laid on top of a NASA image. But it's on NASA's website, so they were kind enough to publish this as ram stripping, obviously.
Oh man, yeah, I knew I had to wear this shirt for a reason. Always a straight answer. They just like to mess with us. They're like, it's swamp gas from Uranus. It belched out. Did you read the story the other day where Uranus launched out a fart or a gas bubble that was bigger than Earth?
Yep. Whoops.
Oops. Sorry.
Yeah.
It's like when you're in the car all day and you just oh man, it's so funny. I got a friend that's I'm not gonna say who she is, but she let one go. She was outside, right? And she didn't think anyone was around. And she was, there was somebody out there. And she looked at that person and she goes, oh, You know what it's like when you're in the car all day. And the lady looked at her like, that was a
Okay.
good one. You know, you were outside. It's not like you were sitting in a car with her.
Yeah. It's all natural, really.
It's all natural. Dude, this could be this reminds me of a thunderbolt of the gods right here. I mean, this is like something out of a Star Wars movie. Forget about the Death Star. This is I don't even know how to explain it. It just this to me is God. This to me shows there is a divine creator that created all this, and everything seems to work in fashion and in harmony together. This is wonderful.
Well, I think it goes to show that there is. I mean, I certainly believe there's a fractal nature to our universe. We see the same patterns repeating at different scales. And interesting, speaking of patterns repeating, did you see the article? You know, the cosmic web the cube that we talked about.
Yeah.
So there was a scientist who had done a bit of research, and he was looking at the pattern. When you look at this, it sort of looks a bit like mold. And he had studied this particular type of mold, and I forget what type of mold it was. And he was looking at the growth, how it grows, the spores, and how it sort of spreads outwards. And he realized that the pattern that it created matched very much with the cosmic web pattern. And so that they had this beautiful link between this microbe producing a structure which was identical to what we see at a sort of a galactic scale, connecting our universe together. And I thought it was very poignant because it kind of proves this idea that the things do repeat at different scales. I mean, obviously they didn't then make the connection that there was a physical link. No, they obviously ignored the fact that somehow this bacteria was following, you know, whatever the current lines were in order to draw that pattern. But it's like lightning. You know, how does lightning follow and trace that path? And why is it that roots grow in a particular direction? Well, rather than it being random, why couldn't it be that they're following sort of a field line that directs them in certain directions? And that is why potentially you're seeing the same structure in the universe, because those field lines repeat at a bigger and bigger scale. So we see the same patterns over and over again. But I thought it was very interesting because obviously they then denied that it was a direct link. But it was interesting that they even published the paper.
No, that's great. Super glad that they did. Let me ask you a couple of more questions before we finish this up. And I got to say thank you. This is, out of all the presentations that we've done, it seems like they get better every single time. And maybe it's because I'm understanding it more. Maybe it has to do with that. So I just feel more compatible and enjoy it because I can keep up. So but I want to talk about this comment right now. Let me do a quick screen share here. So I'm going to share my screen now. And this is comment C 2019 Y4, found by the Atlas system in December of last year. And I have wondered, because of the mass and the actual orbit of this comet and the timing, could there be more to this than they're telling us? Could this be something that could actually cause some serious damage because of the lightened magnetosphere? The magnetosphere certainly isn't as powerful right now due to the solar minimum that we're in, and the proximity of this. The TEL, hopefully we're not going to be going through the TEL. I did a 2D model on it. It looked like we were, but somebody said, Rex, do the 3D models and you'll see that we should be fine. With that said, if this thing starts to break into a bunch of pieces before it gets here and the orbits start going crazy, combined with the mass, what do you think that this could do? Do you think this could be a problem?
I mean, I'd have to study it in terms of looking at its actual trajectory. Could a comet cause problems for Earth? Yeah, absolutely. I mean, you know, look at Shoemaker-Levy, that comet, and the impact that it had on Jupiter. If something like that were to strike the Earth, then even if you were to ignore the electrical nature of those things, then the physical impact itself, it would be monumental. Then if you add on top of that the fact that this might be a charged body, which is at a different potential to our planet, you know, potentially that could be devastating as well. But the majority, I have to say, the majority of comets don't necessarily sit on a collision path. So I don't know. You'd have to study the movement of this and work out how close it comes to us. I think the idea mostly is that planets have a sort of self-defense mechanism built into them. The fact that they have a different charge potential, and you see it with some of the meteors that sort of fly across, they don't actually impact and they sort of explode in the sky. That could be because there is a charge difference that sort of builds up, and as the comet enters, again, similar to what we see in terms of the comet, that sort of discharging that takes place on the surface of that actually pulls it into fragments and then sort of blows it up in an arcing event. But obviously, if it's big enough and it's traveling fast enough, then at some point that is not going to be enough to sort of protect you. But I don't know. I'd have to study the comet to work out whether it is, because there's a lot of reports about meteors that come within a moon's width of us, and I guess part of the problem is that we are better at seeing them, so we spot them more often now than we ever did before. But the majority of them pass us by. But obviously, at some point, maybe one won't, and then I guess by the time you know that, it's probably too late.
Hello. Whoa, my mute. Man, this thing's freaking out on me now. Holy cow, I hit the mute button, then it went unmute, and then it goes, warning, warning, warning. Aliens have abducted you. This is pretty cool. This is something I just realized too. I wanted to let Leak Project listeners know about, and we'll see if we can get you one of these as well. This is the ultimate herb garden. If you go to seedswithlp.com, get yours. We got your seeds right here. This is really a great opportunity for small spaces because you can have your own garden designed specifically for small spaces. 6 delicious herbs included, as you can see right here. It's so easy, anybody can do it. It even has an app on your phone. So if you forget to water your plants, it's like, water your plants, dork. Get off your butt. Do something. So check it out, folks. Seedswithlp.com. And also check out See the Pattern. Go to See the Pattern, subscribe on YouTube, check out Gareth on Patreon as well. And do you have your own website, or where else can they find your work, Gareth? This has been awesome, man. Thank you.
No, just YouTube. I do post to Facebook and to Twitter as well, but I'm not particularly good with those. So most of the content is on YouTube. I have a Patreon, obviously, to support me through this. And if you're interested in sort of the motions and the movement, in terms of what we talked about last time, the latest video that I've done is very much a visualization of that. So you can try and understand how those motions work and what it would look like if we ignored gravity, if we lived in an electric universe, what would some of those motions look like? I spent a lot of time sort of modeling that, and hopefully it gives you sort of an idea of what the electric universe could give you in terms of a different understanding for the sort of stellar mechanics, as it were.
Right on. Absolutely. I'm definitely subscribed, so I get the alerts via emails as well as on my phone when you do a podcast. And until next time, man, thank you very much. I hope you enjoy your staycation, and I'll see you in a few weeks.
Awesome, man. Thank you.
Thank you. Cheers, Gareth. Thank you, everybody, for being here with us. You are amazing. Be the change the world needs to see.